This video is on Chapter 13, Section 1 of your book. It's part 1 of 3 videos, and this section will be going over dissociation in more detail. We've already discussed the definition of dissociation earlier this chapter as the separation of ions that occurs when an ionic compound dissolves. So we're talking about salts dissolving. Now we're going to take a closer look at the equations we wrote with that definition. The first equation we wrote was with sodium chloride. To show dissociation, we start with the solid salt, so we put an S here for solid, and over our arrow, we write H2O because we're dissolving it in water. All right, and we don't care about water being a reactant in dissociation reactions. From here, we break up the ionic compound into its ion components. We have sodium, so we write Na. Then we find its charge on the periodic table. So we open up our periodic table, we find sodium, which is number 11, right next to my cursor. It is in group 1A. Right, from the main group elements, the A groups, we look at their group number, and we see how many valence electrons there are. Whatever the group number is, that's how many valence electrons they have. Each element wants 8 valence electrons, whether by losing electrons to get a 0 in that group to jump to the energy level before it, or gaining electrons. Since sodium only has 1 electron, it wants to lose that 1 electron and back itself down to the electron configuration of neon. So it's going to have a positive 1 charge. Losing 1 negative electron gives it a positive 1 charge. So we go back here and we put a plus next to sodium. Now that it's dissolved in water, to show it's dissolved in water, we use the symbol AQ to show that it's an aqueous product. And then our other product is chlorine. It's chlorine ion, so we go back to the periodic table. Chlorine's in group 7A, right below fluorine. 7A means it has 7 valence electrons, meaning it needs to gain 1 more electron to get 8 electrons. When it gains a negative electron, it gains 1 negative charge. So chlorine is going to have a negative 1 charge. Again, it's going to be aqueous because it's dissolved in water. We still have to balance these equations, so we look how many sodium atoms we have over here, how many we have over here. We have 1 of each. Okay? Here, you're looking just for subscripts. Okay? Any number with the charges is the amount of charge, not the number of subscripts. And we look at this and say, okay, if we have 1 formula unit of NaCl, write that down, means in solution, I'm going to have 1 sodium ion and 1 chlorine ion, or I'll have a total of 2 ions in the solution. So 1 formula unit of NaCl gives 2 ions in solution. If you look at another example here, we have calcium chloride. It's solid to start, and then we put it in water, just like we did with the sodium chloride. And now we have calcium and chlorine. From above, we already looked up chlorine. It's a negative 1 charge. It's now aqueous. If we look at calcium, calcium is in group 2A, number 20, so it has 2 valence electrons. It's much easier to lose 2 electrons than to gain 6, so it's going to lose 2 negative electrons, becoming positive 2, or the positive 2 charge. So we say Ca 2+, we call it aqueous, and then we balance our equation. This time the equation's not already balanced. Over here I have 1 calcium atom, over here I have 1 calcium atom. Again, that 2+, that is the charge. That does not tell us how many calcium ions there are. Okay? There's assumed a 1 down at the bottom as a subscript, so there's only 1 calcium atom. On the left side we have 2 chlorine atoms. On the right side we only have 1. So to fix that, I have to put a coefficient of 2 out front to get the 2 chlorine atoms on the right-hand side. You'll notice when we balance this equation that not only did I balance the number of atoms on each side, I also balanced the charges on the right-hand side. Since this is an ionic compound, the charges should already be balanced, and this is assumed to be neutral. But when you're looking at the individual ions on the right-hand side, I have a 2+ here with calcium, so I have a 2+ charge, and the chlorine, I have a 1- charge, but I have 2 of them. So I multiply that by 2 and get 2-. 2+, or +2, plus a -2 is 0. My charges cancel. If that's not the case, then either the equation is not balanced properly, or your original formula was not written correctly. Because when you write this formula, you need to balance the charges to begin with. If we assume that 100% of this compound dissociates, that means all of the ions, all of the calcium, all of the chlorine separate from the others as it dissolves, you can use mole ratios to determine how much of each aqueous ion is produced. Now we'll do an example problem on how to use mole ratios when we assume 100% dissociation. If I have the problem that says, write an example here, how many moles of sodium and carbonate ions are produced by dissolving 2 moles of sodium carbonate. What is the total number of moles of ions produced by the same amount? Okay, so this is a problem with 2 questions. So first we need a balanced chemical equation. We're going to use the equation for the dissolution and we're going to balance it. So first we have to write the equation for sodium carbonate. If you recall, I give you the polyatomic ions. So carbonate is CO3 with a 2- charge. Sodium, we know from just looking up on the periodic table, is Na+. So you can write that off to the side. All right. When you figure out the formula for an ionic compound, remember you have to take whatever the number is with the charge and cross them. Okay. Now, the 3 is not affected. That sticks with the O always. CO3 must always stay together. If you have to add a charge, you put the CO3 in parentheses and the charge on the outside. So we end up with Na, that 2 comes down, CO3. Since it's just going to be a 1 outside, I don't need the parentheses here. For dissociation, I'm just going to draw my arrow next with water over it. And then I'm going to break my ions down. Well, I just said Na was plus, and CO3 had a 2 minus charge. So now all I have to do is balance. Na, there's 2 of them on the left side, there's 1 on the right side, so I have to put a 2 out front. And the carbonate ion, I have 1 on the left side, 1 on the right side, and that's fine. And my charges do balance out. I have 2 plus and 2 minus. From there, I solve this just like any stoichiometry problem with mole ratios. I start with the 2 moles that they give me, 2 moles of the sodium carbonate, set up my grid. I want moles of sodium carbonate to cancel, so I put that on the bottom. Always put your units in first so they all cancel. And I want to get to moles of sodium first. Well, it's moles of sodium, moles of carbonate, and then total moles. So I'm going to go to sodium first, and I get my mole ratio. There's 1, you get the mole ratio from the coefficient, so there's assumed to be a 1 here, so I put a 1 with sodium carbonate, and there's 2 with sodium. Now I just multiply across, my moles of sodium carbonate cancel, I get 4 moles, and that should be a plus there, 4 moles of Na plus. I do the same thing for carbonate. I start with my 2 moles, Na2CO3. I keep the mole of Na2CO3 on the bottom because I want that to cancel. I go mole CO3 2 minus on the top. I have a 1 here again, and there's a 1 in front of the CO3 2 minus. So I get that I have 2 moles of CO3 2 minus. Then it asks for the total number of moles of ions. So I have 4 moles of sodium ion, 2 moles of carbonate ion for every 2 moles of the sodium carbonate. So all I have to do is add those together to get the total number of ions. It doesn't care what the ion is, it just wants the total number of moles of the ions. So I end up having a total of 6 moles of ions in solution. And that's the end of our discussion on dissociation.